I'm going to start from the basics, logging in, and show a little bit how we view or learn more about ITS inside ITS. And then I'm going to start the Hello World coding. So I'm going to use the SDF public ITS. I'm going to use a plain, normal terminal window and just use telnet to log in. So we're connected to an ITS terminal line, and we type Control-Z to log in. We type a new fresh username. So the first thing here is that ITS complains there's no mail file. That's because we don't have a directory yet. So let's create a directory for this new random user. And we use this little complicated command to do it. These new UDIR words are a little bit magic, and we seem to get an error, but if we go to that directory and type listf, we see that we do have a new empty directory. So if you don't know anything about ITS, you can still learn about it from inside ITS by using the info command. In here, we actually have a lot of information. This program is very much like the GNU info program. So if you know those commands, they are the same here. So for example, I type M to select one of the items. For example, new user. And you can see there's an intro. And this describes the basics, how you use ITS. But today, we're going to do programming. So we can see a little bit about programming information. So you can see we have information about the editor TCO, we have MacLisp, we have Midas, the assembler, and we have an introduction to PDP-10 programming that's called PDP-10. So let's just take a little look there. So this is a nice introduction to the PDP-10 and the machine language. I'm not going to go into detail today. I'm just going to do a little quick live coding Hello World program. So we exit info and we start Emacs. So as you may know, Emacs comes originally from ITS, and actually ITS today is still very much like it was back then. So it's kind of like 90% the same. So if you're familiar with Emacs, you should be right at home with ITS too. So I'm going to load a file. Let's call it hello, and use the greater than character. That means we start we use the ITS file version numbers. So this will increase every time we make an edit. So I'm going to start making a very small assembly language program. Programs usually have titles. So we say hello world. We usually have a starting address. Let's call it go. And we must have an end statement, and we can say add the start address there. This is a very small skeleton program. I save it. We can see we have hello 1, the first version of the program. So I exit Emacs. I'm back to this prompt, which is the debugger, by the way. It's also the shell, like the Unix shell. So it's a shell and debugger combined. So now we're going to assemble this small program. We type :Midas, and we can just type hello, and it will pick the latest version. So that's quick. The program has been assembled. We can list the files. I will use, as you can see, I start the commands with the colon. That's called the colon commands. I will use a few of them at the beginning, and then I will shift to the DDT commands, which are mostly just control characters. So listing files, we can see we have the hello1, the source code, and we have hello bin, the binary output. So let's check this in the debugger. For this, we have to create a job that's like a process in ITS speak. I'm going to use the colon command, :job. And we can type this Harry. By the way, if you see $, that's me pressing escape. So double escape V. Here are all the jobs I have currently. So I have Emacs in the background, and we have hello, which is just empty now because we haven't loaded anything. So I'm going to type :load and hello bin to load the newly assembled program. There shouldn't be much here yet, but we can check go equals, gives us the value of the symbol. It's 100. That's the default starting address for Midas. And we can type go to try to execute it. That failed because there's nothing there. MPV means memory protection violation. That's kind of segmentation fault. So we can check the contents, and it's just types question marks because we don't even have that virtual address yet. That's just completely empty, except for one thing. We do have these for 16 locations. So this is just typing out the address / and the contents at that location. So we can see we have 16 locations containing 0, and that's just the accumulators. The PDP-10, it has 16 accumulators. That's just registers in modern terms. And they are just 0 here because we haven't done anything with them yet. I'm going to type kill to remove this job. And you can see DDT types out Emacs $J. It's just to say that the current job is now Emacs, so we can continue that. So we're back in Emacs now. We don't even have a virtual address space yet, so let's just type something there to get some memory locations. And I assemble again, and this time I'm going to use the DDT command to create a job. So I type hello escape J. And as you can see, we have Emacs and hello again. It's a fresh hello job this time. I'm going to use the DDT command escape L to load the binary. And this time we do have something at the starting address. It's just 0 everywhere so far. I'm going to remove this job, this time with the DDT command escape, Ctrl-X, and dot. Kind of weird, right? But it's very convenient to type. So we're going to do this, make a real program this time. The .logout is a system call that tells ITS to log out. And this 1 comma means just kill this job, don't log out the user. That's not what we want. So I'm going to assemble this again. I'm going to create a job. I don't even have type to type hello bean here, because that's the default for a fresh job called hello. So I can just type enter. And as you can see, DDT knows we have the .logout system call here. So I can execute this. That's :go. But let's just use the DDT command escape G from the beginning here. So we see :kill. That means the job executed and got killed. And now we have just Emacs waiting for us. And I'm not going to type :continue this time. I'm going to type escape P. Let's proceed. Okay, so we have kind of an empty program here. We are going to do some output, right? I'm going to name a symbol, because we are going to use the .open symbol call, system call. We want to use open channel, an output channel, and it's just a small number. It's kind of like a file descriptor in Unix, but we specify the number instead of getting it back from the operating system. So we're going to open channel 1, and here we are going to type the file or device to open. In here, we first type .uao and quote mark TTY. The UAO part, that's the file mode. It means unit ASCII output. Which means unit means write one character at a time. ASCII means, use text. And O is for output. And these double comma means we are specifying 2 half words. Inside this bracket, we have a full word, but the left-hand part is the file mode, and the right-hand part is the device name. And these brackets, that's a very convenient part of PDP-10 assembly syntax. That means we want to have an address here, but we don't really care about what address it is. So it means it's going to end up where we type constants. And the expressions inside the brackets are going to end up in here. This is very convenient and used quite often in PDP-10 programming. Many system calls use so-called skip returns. That means if this system call is successful, it will skip the next instruction and proceed from the second instruction. So we have to handle an error here. Common way to do this in ITS is the .value symbol call, system call. It just means to return back to the debugger. So actually, let's make this an error the first time. There shouldn't be any TTX device, so this should fail. I'm typing Ctrl-L sometimes to clear the screen. So let's assemble this new version. We have the old versions still there, 1 through 5, and the new binary file. So we have this loaded. Let's see it in the debugger. Let's check out the Go, the start address. We have the .open system call. We have .value and the .logout. So that's the entire program. Then we have the constants from the bracket. So let's try this in the debugger. I'm going to type escape 0G to start it, but stop at the first instruction. So we are at the .open system call. You can see DDT also helpfully types out the contents of the address we passed to .open. And that looks strange, right? But if I type a single quote, DDT will convert it to the 6-bit ASCII subset, and we can see the TTX string we passed in, so that looks right. So let's single step this. And we did end up, we didn't get a skip return, but we got the .value system call. So we can execute that, and we just see .val 0, which means we're back in the debugger. This .value is quite interesting in itself because it's used to return any string back to the debugger, and it can use to actually execute any debugger command for us. So for example, we can type an error, this colon $, that's really colon escape. That's the weird DDT comment. Oops, sorry, this should be an ASCII string. So let's try this. Let's just run it and see what happens. Yes, we did get that string back to the debugger. So let's get rid of that and go back to the editor. Actually, that's a better way to handle system call errors, and that's the .lows system call. It can do various things, but let's use this cryptic %lssys constant. Let's try this. And we see that DDT now can type out the exact error message, no such device. And that's what we did expect, because there's no TTX device. So let's replace that with something that does exist. Yep, seems to work. Let's just single step it to .open. Okay, fine. Skip return, so we are at the .logout. And it kills itself. So we only have Emacs now. Okay, we should be doing some output. And for that, we still need to use some accumulators. They're just low-numbered addresses. Or actually, they're proper registers, but they're in the address space at the low end. And we usually call them by name, not number. So the common way is to name them ABC. So I'm just define 3 symbols to use as registers. And now we need a pointer to the string, right? So we make a label hello and a 0 terminated ASCII string, hello world. Now let's include a line break too. this slash, it could be anything. The first character after ASCII C is the terminator. So we start the string here and end it here. So we're going to need a pointer into the string. And now you should understand that the PDP-10 is a word addressed machine. So we can't take an address into a string really, but since the PDP-10 also has the byte instructions, it can point to characters. It just needs more than just an address to do it. So we're going to use this half-word notation again. The right-hand part is the address pointing to the string. And the left-hand side, that's needs to specify the position and the size of the byte. So in this case, we need to point to the very first character, right? So that's position 29, but that's 35 in octal. The PDP-10 usually uses octal by default, so all numbers will usually be octal. So 07 means 7-bit bytes, because the PDP-10 usually uses 7-bit ASCII, and will point to the very first character in the string. And we have that moved to accumulator A. So now we need to load that first byte. That's the LDB instruction, load byte. We're going to load from the byte pointer in A into the accumulator C. And we want to see that on screen, so we use the .iot symbol, so system call. We specify the I/O channel, the TIOC, and the accumulator that has a character C. Okay, so this should actually type out something. Okay, so we have that loaded. Maybe just single step it, just to be sure. I'm going to clear the screen and start at the first instruction. So we have the open call. I'm typing Control N to move on. We have the move instruction. As you can see, it says move TIOC because TIOC has the same value as A. But that's just a matter of presentation. So I'll single step this. Now we should have the address, the byte pointer in A, and we're about to load the first byte. Control N. We see that we have something in C, and it's this weird expression, but we can type the hash mark to have it converted to ASCII, and we see that is the lowercase h, so that looks good. Now we're going to try to use the IoT system call, and we can see indeed there's a small lowercase h there. And finally, kill the job. So that seems to work. So we need to make a little loop to output the full string. The jump instruction, there is a jump instruction, but for some reason, which we don't need to go into here, the usual jump instruction is called JERST. So we're going to loop back to the load byte instruction. And we now need to load several characters in succession, right? So we use the increment and load byte instruction, ILB. So that does the increment of the byte pointer first. So we actually need to have the byte pointer point one character more before the first. And we can actually just have the position point outside the word. This is perfectly legal. The increment will advance the position 44, that's 36 in decimal. So we will subtract 7 from that to get 29, which is the first position in the word for the byte. So this should load the first byte, and if it's 0, the string is empty, or the end. So we're going to jump somewhere, jump E. If C is equal to 0, we can just jump right to this logout system call. We use this bracket constant again.
You have a wrong label on the Durst.
Oh, right, thanks. That should be nice in the debugger, but yeah, we can make it right from the beginning. Okay, so this looks like it should work, right? Load the byte pointer, get characters, check for 0, output, and loop back. Yep, should work. Let's just run it. Yes, we do get hello world. And if you want to see the full program, the DDT version, we can check it here. Open the Go location and see it all. Here we have the hello world string, which looks like DDT assumes it's PDP-10 instructions, but if we type double quote, we can see the text as well. So there you have it, the first simple hello world program. And we're about at 30 minutes, so I think we'll end it there for today. Any questions so far? No questions? Everything perfectly clear? That's great.